Once again, welcome back to the course on cryptography and system security. We were talking about advanced encryption standard algorithm, right? So I'll quickly revise the concepts or the parameters which are related to the advanced encryption standard. First of all, it is proposed by Rigendel, and it is a block cipher encryption technique. And the size of the block is 128. The different variants, right? 128. And the key which is used depends upon the key which we are selecting, the number of rounds as well as the key which will vary, right? In case if it is a round 10 or 10 rounds, which is 128-bit key, and in case if it is 12, again which is 192, and in case if it is 16 rounds, 256-bit key. And so if I select a 10 rounds advanced encryption standard, right? So first there is a term called which is state array. What is meant by this state array means the entire 128 bit of information which are going to be placed in the state array where we have 16 byte of information. Mute yourself, all of you. 16 byte of information, right? And here we are going to process the information in terms of bytes, right? Each byte will be 8 bit, so total 888. So here we'll have 32, so total we add all this, we'll get 128 bit. Once if you have the information or the input in the state array, and then we'll be performing 10 rounds of operation. And for that, so we need to have the number of keys will be number of rounds plus 1. So as for my example, if I'm taking 10 rounds, so I need to have 11 keys where my key size is 128. So 11 into 128. So this 128 key which can be represented in 4 words, where each word is 32 bit, and followed by, in each and every round I'll be performing 4 operations or 4 transitions. The first one is substitute byte, and followed by shift rows, and the third one is mix columns, and the fourth one is add round key. So this is an operation performed in each round. Sorry, these are the operations performed under each round. So when it comes for the last round, there will be only 3 operations except mix column. Before to that, prior to the round 1, we'll have add round key with the plain text. I hope this is clear, right? Also explained about what are the detailed operations or detailed transition performed each and every transition. What is substitution byte, shift rows, and then mixed column, and then add round key. In order to understand the mixed column operation, right, I'll explain about the finite field arithmetic, and then you will be more clear how the mixed column operation is performed. Shall we proceed with the next? Any queries regarding the concept which I explained, advanced encryption standard fundamentals? Any doubts? You can write in the chat box. Okay, if you're clear, then I'm free to move to the next. Here, what I'm trying to explain here is that, so here, I'll be explaining about the GF, Galileo's field, which is a part of finite field arithmetic, right? When we talk about the Galileo's field, which is out of 2, in that cases we'll have only the 2 prime field, which is belongs to this Galileo's field right here, which is 0 and 1. When we talk about the Galileo's field of 8, so here we'll have the 8 combination, which is 2 over 8, right? Suppose if I take any simple polynomial values, which is ax square plus ax plus 1, right? Where I have the three values, 2 power 3, right? Which I have the 3. I started from 1 and ax plus, suppose if my a value can be any values, whether it may be a 0 or 1, whatever it may be. Like I'll take a different color so that you will get more clear. I'll take a blue. Okay. So here, so there's the combination of this 8 value which will start from 0, 0, 0, 2 and 1, 1, 1. If I substitute all the values instead of a, the variable a, right, what I'll get 0x square plus 0x1, sorry, 0x plus 1. 0 into x square will get 0 plus 0x0 plus 1 will get the result 1. Again, when it comes for the 0, 0, 1, so here I'll get the results, which is here also I'll get 1 only, right? Again 0, 1, 0. Again I'll 0x square plus 1x plus 0. Here I'll get only x. When I substitute these values in the place of a, I'll get 0x square plus 1x plus 1. I'll get 1x or x plus 1 for this. This is for this again. This is. I hope this is clear. When I substitute the last values, which is 1x square plus 1x plus 1, I'll get x square plus ax plus 1. So this will be the, so these are the prime fields for the Galileo's field, which is 2 power 8. Sorry, 2 power 3. I'm talking about 3. Sorry, this is only for 2 power 3, not other things, right? When you talk about the values of 2 power 3, where we have the 8 factors or 8 fields, I could say that, which might started from 0, 0, 0 to 1, 1, 1. I hope this is clear, right? So the entire value which I have explained, right? So here the first I just did the mistake, right? Instead of 0, I should have substituted 0, right? Otherwise the rest are fine, right? The same which I explained so far. Right now, what I'm going to explain further is that, right, I just need to explain the list of operation to be performed with these values, the polynomial additions as well as multiplication with the Galileo's field, right? So for example, if I'm taking the two values, 1x square plus ax plus 1 and followed by that 1x square plus x plus 0. And if I do the addition operation, right, which will be an addition will be automatically which is an XOR operation here when we talk about the polynomial. So here all the operation which are in terms of XOR operation only. And we know that when if the two values are same, the XOR operation which will produce 0 as a result, right? 1 and 1 will get 0, 1 and 1 will get 0, here 0 and 1 will get the results 1. I hope this is clear. I hope you are very clear with the XOR operation, right? The XOR operation, right? We will be repeating or we will be studying repeatedly throughout the subject because that is an operation which will be performed for most of the cryptographic techniques because it is reversible. Very similarly, when we took some other additional example, which is x square plus 0 plus 1 and x square plus x plus 0. So here it is 1 and 1 will get 0 and 0 and 1 will get 1 1x and then 0 plus 1 here will get 1, so that will be the results. And we need to make sure that when we perform this addition or multiplication operation, right, whatever the result we are going to get, and make sure that so these results are to be the part of this GF 2 power 3, which are the 8 resultant value which we calculated. So here we arrive the value which is x plus 1 and make sure that whether it is x plus 1 which is present in this prime field. Yes, it is available. So we are free. And when it comes to the multiplication, all right, so this is a simple multiplication. Through that you'll understand the 2 power 3 multiplications. This is a polynomial equation which is x square plus x plus 1, and so this value has to be multiplied by x square plus 1. And if I take the first element, which is x square, so x square plus x square, which will be x power 4, and x multiplied by x square, which will be x power 3, and 1 multiplied by x square, which will be x square. I hope this is clear. X power 4 plus x power 3 plus x square, and so the 1 has to be multiplied by this over the entire term, which is again x square plus x plus 1. So when I do all these values, right, so these two values, when I do the XOR operation, if I have the similar terms, which is x square will get cancelled, right? Rest I will have this x power 4 plus x power 3 plus x plus 1. So this is my resultant value. I need to make sure that whether this resultant value are the prime field of 2 power 3 Galileo's field, right? We'll make sure that what is my value, which is x power 4. I didn't see any value which start from the x power 4 from the prime field of this 2 power 3. So there is no such values. So it has only this x power 2. That cases, right? So this term, which is called irreducible polynomial, I hope this is clear. Any queries regarding this? Right? If this is the value, in that cases, what you need to do is that again, you need to simplify this, or you may need to reduce this equations into the resultant value, which be the part of this, the prime field of 2 power 3 Galileo's field. Right? For that, so the standard formula, this is again irreducible polynomial. Whatever the results we calculated, so that has to be divided by this factor, which is x power 3 plus x plus 1. So this the factor, the equation, the polynomial equation, which is standard, so that the entire value which will become the prime field of 2 power 3, right? So I was explaining about this, the entire result, which is x power 3 plus x plus 1. If I divide this value, so here, if I consider this value, so here it is x power 4, which is 1, and followed by x plus 3, which is 1, and there is no x power 2, so that I could consider as a 0, and followed by x value is equal to 1 and 1 value is equal to 1. So 1, 1. So 1, 1, 0, 1, 1, and this has to be multiplied by this irreducible polynomial, which is p of x, which is x power 3 plus x plus 1. Let's assume this 1. So here we have x power 3, which is 1, and there is no x square. So I am just replacing with the 0. And for x value, which is present, I just represent it as 1, and followed by 1 is present, I can represent it as 1. So 1, 0, 1, 1, right? If I divide this values 1, 0, 1, 1, again here also we are performing the XOR operation. If the results are same, here I'll get 0, 1, 0, 1, 0, 1, 1, again 1, 1, 0, right? And followed by this will be for another round. And so these are the three values, and followed by 1, I am going to bring it down. And again, if I multiply this, if I divide this value 1, 0, 1, 1, I need to find out the XOR operation 1, 1, which is 0, 1, 0, 1, 0, 1, 1, and 1, 1, 0. Let me understand this, or let me convert this result into the polynomial terms, which is 0, 1, 1, 0, which is this is one value 0 plus this is x. Now this is x square. What is this value, which is x square plus ex, by ignoring the 0 value. Now let me check whether this value are being the part of the 2 power 3 prime field. So x power plus ax. So this is the part of 2 power 3 prime field. So I could consider this is an acceptable result for this multiplication of two polynomial equation comes under this Galileo's field 2 power 3. I hope this is clear. Any queries regarding this explanation part? Okay, similarly, I hope this is clear, right? Similarly, right, if you multiply about the values, right, the same concept which I explained, right? When we talk about advanced encryption standards, now I just coming to the actual the requirements, right? I need to explain about which is 2 power 3 because all the when we talk about advanced encryption standard, each byte which has 8-bit values, right? The state array which are represented using a 8-bit values. For that, I need to use a Galileo's function, sorry, Galileo's field, which is 2 power 8. So I will have how many combination, which is I will have the 256 combination, which might have started from all zeros to all one. When I substitute all the values in the corresponding position, the first will be 0 and followed by 1 will be x and followed by this x plus 1. If substitute all the values in the place of x equal a is equal to 1, in that case I will get this entire equation which is x raised to 7, x raised to 6 and followed by till plus 1. I hope this is clear. The same concept I explained with respect to the Galileo's field 2 power 3. Similarly, you have the 256 prime field combination when it comes for Galileo's field 2 power 8. So what we'll be using in the advanced encryption standard operation. I hope it is clear. Any queries regarding this slide explanation? I'm waiting for your acknowledgement. Thank you, Abid, for your timely response. Right, I'll proceed further. Very similarly, when we talk about the multiplications again, so here you can perform all types of addition as well as multiplication with respect to the 2 power 8 values, right? When you talk about this addition, so this the first example which represents the addition example with this 2 power 8, the polynomial equation. The first equation will be x power 7 plus x power 5, which is x plus 1, and followed by the second equation will be x. Other than this, if the both the values or both the coefficients are equal, in that case, so this term will get cancelled and that will become null or void. I could say that due to XOR operation. How these terms are get cancelled? Because if we perform XOR operation 1 1, which will be 0, so I can ignore this part. So x power 7 plus x power 5 and then plus 1. Very similarly, when we multiply this entire value, this x power 1. So this is the equation 1 and this is equation 2. With multiplying this, again x power 7, x power 6. And so this was the last part of or the last field of 2 power 8. And if it is multiplied by x plus 1, first I will take x and multiply all the values. So I'll add the power with 1. So x8, x power 8, x power 7, x power 6, 4, 3, 2, 1, and followed by, I suppose if I multiplied with 1, again I'll get the same value, which is x power 7 plus 4, 3, 2, 1, right? You can simplify all the values, whatever which is exist, right? 7, 7, 7 get cancelled, right? 7, 7, 6, 5, 4, 3, 2, 4, 3, 2, 6, 5. What else is remaining? Again, ax and x will get cancelled. And what are the terms which are still persist? Which is x power 8 plus 1. I hope it is clear. Can you able to follow me? What I'm explaining? Just let me know if I'm explaining little fast. I'm just going little fast because I explained the basics with respect to the 2 power 3 example. If you are clear with the 2 power 3 arithmetic like addition and multiplication, so you'll be easy to understand. Right, further. So here I got the x power 8 plus 1. So again, so we need to understand this, whether this is the part of the prime field of 2 power 8. Definitely it will be not, because the maximum term which has started from x power 7. So here it started x plus 1. So we need to reduce the value using the reducible term, which is, so this is what the pre-calculated values which has to be divided. So x power 8 plus 1 value which has to be divided by this term. There are certain standard values which has to be used for the division, right? So if I represent this in the binomial values, binary values, right? Again, x power 8, which is 1, and followed by there is no x power 7, 6, 5. So I can represent the 3 bits are 0, and then x power 4 is present. So 1, x power 3 is present 1, and there is no 2, x square is not there. So I can represent it as 0, and x is present. So I can represent 1, and then this 1 as it is, right? Now I'll divide this x power 8 plus 1, which is x power 8 plus 1, which can be represent the first letter and then last letter, which are going to be marked as 1, and the remaining letter which are going to be 0. 1 0 0 0 0 0 0 0 1. I have added one extra 0, right, which has 4 plus 4 8 bits, right? Now this entire information which has to be divided by this 1 0 0 0 1 1 1 1 triple 0 followed by 1 0 double 1. If you do the division operation, right, we'll get these results, right, which is x power 4, x power 3, and then x. Now we can check so whether this is the part of 2 power 3 8 Galileo's field. Definitely this is the part, because it has started from x power 4 and then x power 3, x power 6. So there are 256 combination under this 2 power 8 GF. So it is starting with the x power 4, definitely. So this will be the part of this prime field of 2 power 8. So let's assume this is the result. I hope this is clear. Any further clarification required on this? So whatever the concept which I explained, which are belongs to the finite field arithmetic. Is there any further clarification required on the topic? Okay, if I continue with that, the advanced encryption standard, I was explaining about the mixed column operation. When we talk about the mixed column operation, I'll elaborate further if you are clear with the mixed column operation. So this is how we can perform the mixed column operation based on the values which we considered, right? Suppose if you have the example, right, D4, this is what the value which is stored in the state array, and multiplied by the any constant value, which is, right, D4, and then D4 BF 5D30, and then 230101, right? It is a 4 cross matrix, and so this is also a 4 cross 4 matrix, right? We can consider the first column, take the first column value and the first row value, right? If we use the simplification operations, right, what I explained so far, right, and based on that, how this multiplication can be done using the GF 2 power 8, you will get the results, and followed by this you will get the 4 results, and if you are simplifying the results, you will get the final result that will be stored here, right? So this is an example to understand how the multiplication has to be done when we talk about the mixed column under the advanced encryption standard. So here, in order to do the multiplication of the two hexadecimal values, so we are going for the finite field arithmetic. That also according to the example I'll explain again in the next slide. Similarly, the second term, which is BF and 03, again the same multiplication similar to the what I explained just now. Again, so it will produce the 444. I mean, the four output each are the 8-bit and results, 8-bit, 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 and finally, if you are XORing all the results which we calculated, and finally we'll get 8-bit results again. So that is going to be represented using again a hexadecimal value, which might be depends on the calculation we did, right? So again, the add round key, which I've explained in the previous slide itself, right? Okay, if you want, I can explain it again, right? The add round key, which will be the simple XOR operation, which is 04, which is 0 0 0 0. When we talk about 4 1, sorry, this is 0 0 1, or this is 1 0 0, right? I could erase this. I just mentioned it. What is the value for 1 again? So here use 0 1 0 0. So 1 to 4 again. When we talk about the A0, so this the corresponding the state array value which are to be XORed. So here I'll assume it is 0 0 0 0. Again, what is the binary value for A, which is 10. So 10 means 8 and second position are going to be the 1, right? So 1 2 4 8. So 8 plus 2, which is 10. If I XOR these two values, here I'll get 1 0 1 0 0 1 0 0. What is this 1 0 1 0, which is corresponding again A, and followed by this 1 0 0, which is 4, which is A 4. I hope this is clear. Are you clear with this add round key operation based on the hexadecimal XR values, XR operation? Okay, so if it is clear, then I'll move further. This is again the simple operation, right, based on the value which I've selected, right, again. So whatever the concept which I explained so far, right? So again, the simplification, the values, right, using the GF functions, multiplications. Suppose here, let's assume this is my the first. I just take it in the reverse way, right? I took the column from here, and then if it is a row value, so it is 63 multiplied by 02, right? Very similarly, if it is 02, it is the corresponding binary value, and then 63 is binary value, right? And if I multiply this value, I'll get this coefficient, right? If I map with the corresponding values, I'll get C6, right? Now, whatever the value which I multiplied, which is 02 into 63, which is C6. Similarly, I have to do the multiplication for the remaining terms. It's a bit complex operation. That's why this algorithm, which is more secured, because it involves a lot of mathematics. Even if there is a change in the one bit, the entire ciphertext, which will be completely different from the actual information, right? Similarly, we need to, so this is, if it is, this is Cx, very similarly, we need to find the value for this and this and this based on the GF field 2 power 8 polynomial multiplications. I hope this is clear. If you're performing all the values, so finally we'll get the results. So that is going to be stored in the state array. Okay. So this is again detailed explanations, right? You can go through the contents. This is completely based on the concept which I explained, which is based on the 2 power 3 and then 2 power 8 GF, right? And then finally you need to do the simplification, because the result which we derived is x power 8. So I need to reduce with this value, which is the constant value, which is x power 8 plus x power 4 plus x power 3 plus x plus 1, and I'll get the prime field result. What is the results? Sorry, just stop sharing the screen, right? And you can go through it. If you want, I can share it again. I can explain it for a bit further. But the concept is going to be the same, which I explained based on the 2 power 3 and then 2 power 8 Galileo's field. I mean, the finite field arithmetic operations. Any queries regarding the contents which I explained in this the 3 sessions? So it's a little big topic, but it involves a lot of mathematics, including the finite field arithmetic. That was the little tough part. But once if you are clear with the simple polynomial addition and multiplications, so after that, that will be a little easy. The thing is that you need to do more practice, then only it will become so clear. I hope you understood the concepts, and if you have any further queries, you can write in the chat box. Any queries regarding the contents which I explained in this 3 sessions? Advanced encryption standard. With this, so we are coming to the end of advanced encryption session standards. In the next session, we'll be discussing about the further public cryptographies. Maybe we'll continue with the RSA algorithm, which I covered during the practicals, or else we'll go with the Diffie-Hellman key exchange algorithm or Elgamal public key algorithm. So if there are no more queries, then we'll end the session. Until take care, bye-bye. I hope all of you wrote the attendance. If not, I'll wait for a second or maybe a few seconds. Quickly can write in the chat box. If everyone done with the attendance, then I can end the meeting. Okay. So I hope all of you wrote your attendance in the chat box. I'm ending the meeting. Okay. Take care.